Alright, 6.3 part 2 is really just the bridge between what we're going to do from what we did, the counting rules in 6.3, to what we're going to do in 6.4. Alright, 6.4 is the last chapter, but it's a big one. There's a lot in 6.4. Alright, so 6.3 part 2 is getting you to, again, use the same rules that we did in 6.3. You picking among different alternatives. If you use the word or, we add. If we're doing a sequence of events, a multi-step process, you use the word and, you multiply. What we're going to focus on specifically in this case is the difference between when you're allowed to repeat and when you're not allowed to repeat. All right, that's what we're going to look at. When I can pick the same letter twice, all right, repetition or not allowed repetition. Because in the next section, we're going to look at very specific examples where it's the non-repetition case. So repetition and non-repetition. Alright, so the first option we have, suppose I have a bag full of marbles. Alright, so I've got a bag of marbles in my hand. Alright, the bag of marbles have 5 red and 7 green. Alright, so there are 12 total marbles. 5 red, 7 green. Suppose you pick 3 marbles at a time, right, and in a row. So I've got my first pick and my second pick and my third pick. Alright, so it's and. I pick 3 in a row. We replace the marble. So I take my marble out of the bag. So the first pick, I take the marble out of the bag, I make a note of what color it is, and then I put the marble back. Second pick, I pull the marble out, I reach in and pull another marble out of the bag, I make a note of what color it is, and I put it back. Third pick, I pull a marble out of my bag, make a note of what color it is, and put it back. Technically, I could grab the same marble 3 times. Right? There's repetition in your selections. Alright, so the first one is asking how many outcomes are possible. So what's my sample space? How many total ways can I grab 3 marbles out of this particular bag of marbles? Alright, so number in my universal set. Well, it's a sequence of events, right? I've got 3 picks. I've got my first pick and my second pick and my third pick. Well, in all 3 picks, since I'm replacing the marble, there are 12 altogether. There are 12 possible marbles I can reach in and grab each time I pull a marble out. So 12 for the first pick, and 12 for the second pick, and 12 for the third pick. So 12 cubed, so number in my universal set is 1,728 outcomes total. Now we're going to look at a couple subsets of this. Keeping the same setup, right? Same bag of marbles, same color, 7 green, 5 red. Now we're going to look at some subsets. All right, how many outcomes have exactly 1 red in one of your picks? It didn't say which pick. I get 1 red marble in one of my selections. All right, so a number of ways to get 1 red in 3 picks, which means I get 1 red and 2 greens. All right, but since I didn't know when I picked the red one, right, there are 3 times I could pick the red one. So I sort of have to do it like we did with the sequence with the word computers, and I picked a vowel. First thing we have to do, well, how many ways can I pick a red? And then how many places can I pick the red? And then I need to finish off my group with picking 2 greens. Well, pick a red's easy. There are 5 red marbles. How many places can I pick a red? Sometimes it's easy to list it like we did when we had groups of people together and we figure out the places. I can have the red in the first pick and then 2 greens. So I could have red, green, green, or I could have green, red, green, or I can have green, green, red. Right? And so there are 3 places. I can pick the other way to think about it is the red one can show up in the first pick, or the red one can show up in the third pick, or the red one can show up in the second pick. I think I skipped the second. And so there are 3 ways to do it. Alright, so how many ways are there to pick a red marble? Well, there were 5 choices for red marbles, right? If you go up here and look, I had 5 choices for red marbles, and there are 3 places that the red marble could show up in, right? It can show up in the first pick, second pick, third pick. And then I have to pick 2 greens, right? 1, 2. So the first green marble had 7 choices. Since I'm replacing the green marble after I pick it out, the second green marble also had 7 choices. There's still 7 green marbles in there, right? I could pick the same green marble twice if I wanted to. So I had 7 for the first green pick and 7 for the second green pick. Right, so how many outcomes of exactly 1 red? Well, it's 5 times 3 times 7 times 7. So a number that have 1 red and 2 greens. Well, whatever 5 times 3 times 7 times 7 is. So that comes out to 735 ways outcomes. Alright, so out of the 1,728, 735 of those outcomes, I only selected 1 red marble in one of my choices. Alright, next subset. How many outcomes have no red marbles in any pick? All green selections. So the first choice is green, the second choice is green, and the third choice is green. Alright, so a number of ways to get all green. Alright, no red marbles. Well, green for the first, green for the second, green for the third. Well, there were 7 green marbles on the first one. Since I replaced it, I could technically pick the same green marble all 3 times. So 7 for the second and 7 for the third, so 7 cubed, which is 343 outcomes. So out of my 1,728 possible outcomes, 343 of them are I get all green marbles, no red marbles. Alright, the last one, there's that at least phrase again. At least 1 red marble, so number of ways to get at least 1 red. Well, 1 red marble would mean I could get 1 red, only 1 red, or I could get 2 reds, or I could get all 3 reds come out. And that's fine. If you want to solve it that way, you can. It's actually easier to use the complement. I actually have all the numbers already for the complement. So I'm going to use the complement. Number of ways to get at least 1 red. Well, at least 1 red means 1 red or more, right? I get 1 red or more than 1 red. The complement to that is no reds, right? All green come out. So I want to throw away all of the outcomes where I had no reds. Well, I figured that out in the last example, right? All of them are green. And so it's the number in my universal set minus the number of cases where there were no reds. Again, that's the all green case. Which I actually have those numbers already. Those were found in my first 2 outcomes. All right, so the universal set was 1,728. So there are 1,728 outcomes. 343 of them, right, were all green. Right? No reds showed up in 343 of the outcomes, which means if I throw away those outcomes, if I subtract them, I'm left with all of the outcomes that have at least 1 red. Some of them have 1, some of them have 2, some of them have 3, but all of them have at least 1 red outcome because I threw out all of the outcomes with no red in them. All right, so take your 1,728, subtract away your 433, and that comes out to 1,385. Alright, so that was an example of pulling 1 marble out of a bag at a time where I'm allowed repeats. Well, I'm going to do the exact same example, but this time I'm not going to allow myself to repeat, meaning I'm not going to allow myself to pick the same marble more than once, and see how the problem changes. Alright, so second, same example, but there's a subtle change to it, but it's important. Same bag of marbles. Still has 5 reds, still has 7 greens, so there's 12 marbles altogether. You pick 3 marbles out in a row, but this time you do not replace them after each pick. So it means I pull my marble off, make a note of its color, and leave it out of the bag. I pull my second marble out, look at its color, and leave it out of the bag. I pull my third marble out, look at its color, and leave it out of the bag. So I can only pick 1 marble Right? I can't pick it twice. Right? I can't pick the same marble more than once. Right, so same questions. How many possible outcomes are there? Well, number in my universal set, I still have 3 picks. But at this time, instead of having 12 marbles each time, every time I make a pick, I've got 1 fewer marble in my sack. So I had 12 for the first pick. Right, I picked the marble out, I looked at it, made a note of its color, but I didn't put it back. So in my second pick, there's only 11 marbles. Right, and then after my second pick, I picked a marble out, and now I've set 2 marbles to the side. And so in my third pick, I only have 10 marbles. So this time, instead of 12 times 12 times 12, it's 12 times 10 times 11. So the universal set with no repeats is smaller. It's only 1,320. Right, the other one was about 1,700 and something. All right, so there's the total sample space if I don't replace my marbles. All right, same subsets again, no replacing my marbles. So how many ways can I pick exactly 1 red? So I want 1 red, which means I need 2 greens. No repeats. And so same setup. First thing I have to do is I have to pick a red and then place the red in one of my selections and then pick 2 greens. Well, picking the red marble, there's still 5 red marbles. When I pick a singular red marble, there's still 3 places that red marble could show up, right? I could pick the red marble the first time, or the second time, or the third time. So there's still 3 places that the red marble could show up. Where the problem changes when I pick my 2 green marbles, right? I've got 2 choices that I've got to pick 2 green marbles. The first time I pick a green marble, there were 7 of them. But remember, I don't replace that green marble. And so the second time I pick a green marble, there were only 6 choices. All right, and that's the only difference in this problem versus the previous problem. Right, so it's 5, 3, 7, 6. So it is going to be slightly less than the last example. It comes out to 630. All right, so out of my 1,020, 630 of those have exactly 1 red marble and 2 green marbles. Alright, no red marbles. So next example, no red marbles. They're all green, so number of ways to get all green. No reds. Well, first is green, second is green, third is green. And again, the difference here between what we did before is no repeats. The first green marble selection, there are 7 green marbles, but I don't replace it. So on the second selection, there's only 6 green marbles, and on the third selection, there's only 5 green. And so I subtract 1 each time, because I don't put it back. And so instead of 7 times 7 times 7, it's 7, 6, 5. I multiply it out. There are 210 outcomes. All right, so there are only 210 outcomes with no red marbles out of my total. All right, the last example, again, I'm going to use the complement. At least 1 red. Well, it's my universal set minus the outcomes with no reds. All right, all green. Which I have those. Right? My universal set for this one was 1,320. Out of those 1,320, 210 didn't have a red in it. So if I take those 210 and throw them out of my universal set, what's left over are all the ones that have at least 1 red marble. Meaning I have 1 red marble or 2 red marbles or 3. Without repeats, it's smaller. It's 600. 1,110. If I did my math right, I think I did. All right. 10 away from 2010, 2 from 3, 1. So 1,110 out of my total 1,320 have at least 1. Some of them have 2. Some of them have 3 reds. Some of them have only 1. All right. So that's the difference. So it's important. If I repeat, I'm going to have more options because I have repeating options. If I don't repeat, I have fewer options. Right? And so non-repetition has fewer. And I've taken into consideration, have I already selected one of these? Let's do another example. A professor randomly assigns a 4-digit code for each of his students for the purpose of purpose of posting grades. I didn't say it here, but whenever it's a digit, we always assume digits are 0 to 9. Alright, I've got 10 options for my digits. Now the first one, how many codes are there if I can repeat? So technically somebody could have the same number in the whole entire code, right? I could have a code with the number 2 4 times. Alright, so number of codes when I repeat. Well, I've got 4 digits. Alright, and I can repeat, so each one of those digits has 10 possible choices. There are 10 digits I can choose from, so 10 to the 4th or 10,000. So there are 10,000 possible 4-digit codes if I'm allowed to repeat digits. Well, how does the problem change if I'm not allowed to repeat? So same thing, I'm still picking a 4-digit code, but this time, if I pick the number 2 in my code, I can't pick it again. There's only one number 2 that shows up in my entire code. Alright, so number of ways that I can get my codes with no repeats. Well, I would have had 10 choices for the first. But once I pick that first number, I can't pick it again, so there's only 9 for the second. Now I've picked 2 numbers, I can't pick them again, so 8 for the third and 7 for the last. So each time I have to subtract, right? Because I have one fewer digit to select from as I go down my code. Right, so it's 10,987. Multiply that out. 5,040. And so it almost cuts it in half. It's not quite, because there's that 40 on there, but it almost cuts it in half from repeating to not repeat. So it's a big difference between repeat, I have 1,000 option, no repeat, I have a little over 5,000 options. Alright, on your own, see if you can't do the following one where we could pick different passwords by picking from the alphabet, and the difference between uppercase and lowercase. So that means there are 52 choices, right? I've got 26 uppercase letters and 26 lowercase letters, so there's 52 letters to choose from. And how many difference if you're repeating and not repeating. Again, I'll post the answer to that later. Alright, so that's, again, like I said, it's the getting you to understand the difference between when I'm allowed to repeat and when I'm not allowed to repeat changes the problem. In the next set of notes that we're going to get to, the last set, 6.4, we're going to look at special outcomes, special counting techniques and formulas that actually are built into the calculator that allows us to count whenever we're not allowed to repeat stuff, whenever no repeats are the case. And so we'll get to that in the next set of notes. And it's a big set, there's a lot to it, because there are 2 different ways we can count with no repeats. Alright, we'll stop there.